So now we are talking about our friend, the atom, and nuclear energy. This is one of my favorite forms of energy, and this will bridge into some of the discussion of Einstein's theories of relativity. So we're all pretty much familiar with what we'd call mechanical energy, which is, when we say mechanical energy, we mean what we're saying is kinetic energy, things moving. Okay, just like we call Newton's system of physics mechanics. We're not talking about guys who fix cars. We're talking about objects moving. Mechanical energy. We're familiar with chemical energy in the sense that we're familiar with, if you take some wood and you burn it, the stored chemical energy is becoming heat energy. We're familiar with heat energy. We're familiar with electromagnetic energy, especially when we see light. We know what microwaves are. We know what magnets do. Okay, these are things magnets that we're familiar with. Nuclear, however, is a little more out of our everyday realm of experience. But if it weren't for nuclear, none of us would be here. Because the sun is powered by nuclear energy, the Earth is powered by nuclear energy. And does anybody know what I mean by the Earth is powered? Because the Earth needs power too. The Earth needs energy as well. Yes.
Is it the heat of the sun transfers to the earth and causes all the plants, or the light of the sun transfers to the earth, causes all the plants to grow, as well as heat?
Well, the Earth needs its own. Here, let me give you a quick rundown on how your life depends on clean, natural nuclear power. All right, little lesson in nuclear physics here. So here's your friend, the Earth. That was pretty good. Yeah. It's not perfect, but it's pretty good. Now, inside the Earth, there are many layers. The outside layer we know is called the crust, and in reality, it's paper thin in relationship to the overall size of this thing, but I can't draw that well. So there's the crust, and then you've got all these other layers in there. You've got the core, which is basically nickel and iron, and you've got this thing called the mantle. But there's different layers, okay? And we know all this stuff because we've blown stuff up on the surface and listened to the echo and then put the picture back together. So we know the densities of what's in there, and then based on their densities, we can pretty well figure out what it is. Now, there's a couple interesting things about our planet which are life-sustaining. One of them is that we have around our planet a very handy magnetic field. North, south, and I can draw the field. These are the magnetic field lines coming out of the Earth, wrapping back around, okay, going into outer space. Now, you're all familiar with the northern lights, right? Here's some northern lights, Aurora Borealis and Aurora, what's that one called? The one that's happened in the south? I used to know this. Well, anyway, they happen down there too, the southern lights. They have a name. Now, the magnetic field is useful not just because it tells the birds which way to fly, because birds have little microscopic pieces of iron in cells in their brain that act like compasses. So birds can tell the direction of the magnetic field, and interestingly, it's been shown that they actually see the magnetic field in their vision. So when they're flying and looking at the Earth, they can see the direction of the field. It's somehow they see it as superimposed on their vision. So anyway, that's kind of a side issue, but that's not why the magnetic field is important. The magnetic field is important because it blocks the solar wind. Anybody know what the solar wind is? Okay, solar wind, we'll come back to this picture in a second. Let's go to another slide. So here's the sun. I don't know why it's green, it just is. The sun, as it does its nuclear thing, which we'll talk about, blows off from itself particles, mainly protons, okay? I mean, literally, I don't know if it's millions or billions of tons of protons fly off of the sun every second into space. And these protons, given, if left to impinge on the atmosphere of the Earth, so this blue line represents the Earth's atmosphere. Anybody guess what those protons would do if they hit the Earth's atmosphere?
Would they destroy it?
Yeah, they blow it away. To wit, planets that have no atmosphere have been shown that they don't have any magnetic field. So anyway, the magnetic field does this. Watch. Because of the orientation of the field, here's the spin of the Earth's axis, north, south. The magnetic field of the Earth is aligned with this spin, and it literally makes a shield around the planet that diverts the solar wind like this. Watch. So the solar wind, and why does the solar wind go around the magnetic field? Well, that's because it's a plasma. It's made of charged particles, and when charged particles move in a magnetic field, they experience a force, and that force diverts them around the Earth's what's called magnetosphere, which is the magnetic field around the Earth. And so we are protected from the sun's destructive wind. And it keeps the Earth's magnetic field keeps the Earth's atmosphere from getting blown away. Now, what does all this have to do with nuclear energy? Let's go back to our previous slide. Well, have you ever wondered why the core of the Earth is molten? Anybody ever wonder that? Yeah. Why did you wonder that, Nicholas?
Well, I just wondered why, because it doesn't seem like there's anything keeping it molten. Why doesn't it cool or...
Exactly. Yeah, that's a weird thing, right? Why doesn't the Earth cool off? Well, the answer is there are a lot of elements in the Earth's core or in the mantle that are radioactive. You have uranium, you have thorium, I don't know if it's TH, there's thorium in there, and there's other elements, but mainly uranium and thorium are responsible for this. They're always undergoing the process of nuclear fission, where their atoms of uranium, for example, are splitting up and becoming two daughter particles or daughter atoms. In the process, they release heat. Thorium, same thing is happening. Thorium is breaking apart and generating heat. And there's so much of it, and it's so big and so well insulated in there that the temperature goes up and up and up and up, and the rocks melt, and we end up with molten metals inside the core of the Earth. Yes, Nicholas.
But if those two atoms are always splitting, wouldn't it get to a point where there's so many of them that it explode or something would happen?
Okay, when they split, the daughter atoms are half the size of the original atoms.
Oh. Do they get to a point where
it's not making two thoriums, it's making something else. So they're splitting into they're splitting into other elements, and they're working their way down the chain to lead, which is not radioactive anymore. And then so lead won't continue to undergo fission. So this process will go on for a very, 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 very long time, because so much energy is being released and it happens so slowly that, you know, just like the sun is capable of burning for billions of years, the Earth is capable of maintaining its molten core for billions of years. But what does this have to do with the magnetic field? Well, that is what I will tell you. Okay? So here's the Earth. And here, for example, is the hot molten center of the Earth. And for very complicated, not fully understood physical reasons, this thing acts like a giant dynamo or generator that as the Earth turns, it produces massive electrical currents inside the Earth. And these currents of electricity produce, just like current moving through a coil of wire. So if I have a coil of wire and I run electrical current through that wire, it makes a magnetic field around the wire. Same thing, currents circulating in the Earth makes a magnetic field, and it has to do with the fact that this is molten and the fact that the Earth is turning, and it makes this giant dynamo, and that magnetic field prevents the atmosphere from getting blown away. So if it weren't for the nuclear power of the Earth, the atmosphere would blow away. The other reason it keeps us alive is more of a long-term reason, and it has to do with plate tectonics, where the Earth is always, every once in a while, through volcanic action, is spouting material from the core of the Earth into the atmosphere, and that is, believe it or not, replenishing minerals. Those minerals get eroded by water and brought down to the oceans, and they get subducted back down through the ocean floor into the crust and recycled. So all of the plate tectonics and volcanism of the Earth is powered by nuclear power. Okay? And these things are important for life because they recycle elements. Now, we need to stop this one, and we'll go to the next lecture.